So last today, we've got Kaelan Weiss, who will be talking about the research that he did this summer with Dima Beletsky, James Kessler, and Dan Titze.
Right, so my name is Kaelan Weiss, and for my project, I was assessing the forcing skill for the Lake Champlain flood forecast. For those of you who don't know, Lake Champlain is located in between New York and Vermont. It is the sixth largest lake in the United States behind the Great Lakes. It is 200 kilometers long, north to south, and only 20 kilometers wide, east to west. Its deepest point is 120 meters. On average, it's 20 meters deep. And in recent years, it has experienced rather severe flooding. So these pictures are from 2011, a specifically notable year for Lake Champlain flooding. On the left, you can see houses that are underwater. On the right, that's the Burlington, Vermont wastewater treatment plant nearly inundated, which of course would be a large problem. When this flood occurred, there was no warning system in place. So to amend this problem, CIGLR and GLERL scientists have started to develop the Lake Champlain flood forecast system, which is basically a hierarchy of meteorological, hydrological, and hydrodynamic models that work in tandem to create the flood forecast. And so I've on the right here is sort of a first order schematic for how the flood forecast actually works. On the top are the meteorological models, which provide wind forcing to the hydrodynamic models and precipitation to the hydrologic models. The hydrologic model then provides things like river inflows into the lake. So the hydrodynamic model then uses the wind forcing and the river inflows to model things like waves and lake level, which are the things that you need for your flood forecast. So the important models for my project were the meteorological models, so HRRR and GFS. HRRR is the high resolution rapid refresh model. It's a 36-hour forecast. It has high spatial resolution, and I'll just mention now that HRRX, the next version of HRRR, is set to be operational this fall. So I've included results from that model in this presentation as well. On the other hand is GFS, or the Global Forecasting System, which is a 120-hour forecast, so a 5-day forecast, but that has much lower spatial resolution than HRRR. So the first 36 hours of the meteorological forecast are filled in by HRRR, and then it switches over to GFS to fill out the rest of the 5 days. And those two models work together to provide the 5-day forcing for the operational flood warning. Like I said, the flood forecast is not yet operational, so there are a couple inaccuracies within the forecast. One of those being that the inflows into the lake are too low. Or in other words, there's not enough water entering the lake. That's being showed in this plot here. So this is a plot of bias versus specific river inflow. And bias is just a measure of how much inflow the model is predicting versus how much the actual observed inflows are. So it's the model minus observed. So a positive value means that the model is over predicting inflow or too wet. A negative value means that the values are being under predicted or too dry. As you can see here, most of the major inflows are too dry. So we take a step back and say, okay, is that just because the forcing is too dry? So that leads us to take a look at the precipitation to see if there's just not enough precipitation falling on the watershed. Similarly, another inaccuracy is that the waves and storm surge are too small within the flood forecast. And that's shown here in this figure, which is wave height versus a time series of wave height for just a specific period. The modeled wave height is in red, observed in black. And what we see, especially during these large peaks, is that the modeled is underestimating the wave height. And that's pretty much consistent throughout this entire time series as well. So again, we take a step back and say, is that due to the forcing? So we're going to take a look at the wind coming from the meteorological models. Jumping into how we went about this, starting with precipitation, we basically just compared forecasts with observations. So forecasted precipitation with observations on the ground. And those observations came from the Global Historical Climatology Network, which provide daily precipitation at a bunch of different locations. These are the locations within the Lake Champlain watershed. And then we take all of these and we pluck out the ones with less than 10% missing data from our analysis window of April 2018 to May 2020. And what we get is this distribution of observations. And so on this color bar, green is 0% missing data, yellow is 10% missing data. So we're left with about 40 observation stations and fairly well distributed throughout the watershed. There are a lot over in the central east portion, but fairly well distributed. If you remember from a few slides ago, the inflow results depended on which specific inflow it was. So we're going to basically do the same thing with the precipitation and break the full Lake Champlain watershed up into its sub-watersheds. And those are shown here. The different colors just correspond to different hydrological levels. And the figure on the right is showing which of those sub-watersheds are represented in our observational data. So all of these watersheds have at least one observation station within their bounds. Not all of them are represented, but luckily most of the large ones are. Hopping into the results from this analysis. So this is a daily precipitation forecast scale for each sub-basin within a specific window matching that of the inflow bias. So we have the top panel here is again bias, so model minus the observed values, and this time it's precipitation, so we're talking about millimeters per day. Again, above the 0 line means that the model is too wet, there's too much rain falling, below means it's too dry. And then we have the root mean square error and the mean absolute error as well. The bias gives you sort of a metric for accuracy, whereas the two lower metrics are more of precision measurement. For terms of our analysis, we are looking more closely at bias. So the different colors here represent different forecasts. So in purple, we have the first full day of the HER forecast. In gray, we have the first full day of the HER-X forecast, the next version of HER. And then the rest of the colors correspond to the longer GFS forecast at differing periods into the forecast. So this is the first day, the second day into the forecast, the third day into the forecast, the third day, fourth day into the forecast. And each box plot here, I should mention, one data point in each box plot is one station. And each column of data here, this is a very good, there's a lot to talk about on this figure. Each column of data here represents one of the subsheds arranged by size of the watershed. So what we're actually seeing is that consistently GFS is too wet. It's overestimating the amount of precipitation. HER, on the other hand, is generally too dry, but in some cases, it does fall above the 0 bias line, so it is too wet. But in general, our forecasts are too wet. We can then go back and tie that into the inflow bias, and if we recall, the inflow bias is too dry. And these 6 rivers here correspond to the 6 sub-watersheds here. Basically what we're seeing is that the inflows are too dry and the precipitation is too wet. So there's this disconnect between the inflow bias and the precipitation bias. In general, what we can say from these results is that HER and HER-X are generally dry. The GFS forecast, precipitation forecast, is wet. And importantly, the dry biased inflows do not appear to be caused by the precipitation forecasts. That being said, the precipitation forecast has its own issues as well. Moving into the wind portion of the analysis. So to do this analysis, it's basically the same thing. We're just comparing the forecasted wind values with observations. And for wind, we had 6 locations across the surface of Lake Champlain. 3 NOAA buoys shown in blue here, and 3 FEMC towers shown in red. And so this is what one of the buoys looks like. This is what one of the meteorological towers looks like. And you can see that the anemometers on these two locations are at very different heights. And so we scale the wind speed of the observations to a consistent 10 meters above the lake surface using the neutral stability assumption. That gives us a consistent comparison across all of the observations. It also matches the 10-meter wind output from our models. Here's a summary of the wind observations. So I'm just showing coincident data. So data from which data which is present consistently present for all of the different stations, which just happens to be basically summer months from 2018 to 2020. Those observations are overlaid pretty close to their locations on the actual lake. And they're being shown as wind roses, which if you're not familiar with those, it's basically a radial histogram where the bar points to the direction from which the wind is blowing, and the different colored bins, the size of those bins correspond to how many of those observations fall within these speed bins. So the warmer the color, the faster the wind. What we're seeing is that the observations depend greatly upon where you are in the lake. So in the open lake here, it's fairly consistent between these two locations. Strong southerly winds predominate. As far as the other locations, though, it really does depend on where you are. So for something like down here in this tight channel at the southern end, the distribution is fairly well spread out, and we're getting fairly low wind speeds. Another thing to note is the low GFS spatial resolution. So that's being shown here on the right. So the GFS computational nodes are shown as green dots. The observational stations are shown again as red triangles. And to do the comparison, we basically just take the nearest grid point to the observations and do a one-to-one comparison. HER has a refined enough grid that the observations and the grid point are basically right on top of each other. But for GFS, we see that for something like this station, those observations are fairly far removed, and the grid point very often falls on land. So that's just something to keep in mind looking at the GFS results moving forward. So just like the observations, the results from this analysis depend on where you are in the lake. So there's no real succinct way to summarize all of the results. So we're just going to look at one location, that being Colchester Reef, which you can see is here in the middle of the lake, in the open part of the lake. We're going to look at these because this being like the largest open basin in the lake, it should be the most important for things like for fetch, for wave setup. So these should be fairly important as far as their impact on the actual model, on the wave forecast. The results are broken up into two sections: the magnitude on the left, the wind direction on the right. And again, we have the bias and the two precision metrics down below. This is error plotted versus time into the forecast. And these results are basically averaged over multiple hundreds to even about 1,000 forecasts. What we're seeing is that HER X and gold arrows here are very close to that zero bias line. Below that are the HER forecasts, and even farther below that are GFS results. So all of the forecasts are underestimating wind speeds in the center of the lake, but HER X is definitely doing the best, and the same story is being told with the precision metrics down below. As far as direction, these results are shown as wind roses again. The observational data set is the top left. 24 hours into the HER forecast is shown here. 24 hours into the HER X forecast is shown here. The bottom row is all GFS, but 1 day in, 3 days in, and 4.5 days into the forecast. Basically, what we're seeing is that all of the forecasts are capturing this sort of north-south wind distribution, but all of the models have a very slight counterclockwise bias. And summarized here. So her and her X are about 9 degrees counterclockwise rotated, whereas GFS is about 17, which is fairly reasonable. The conclusions that we can make, again, about the open lake performance of the models is that all of the models underestimate wind speed. Her X has the smallest bias, with GFS the largest. The modeled wind direction is satisfactory, with her and her X being better than GFS again. And importantly, the switch to her X from her will improve the accuracy of the model, which in turn should sort of close that gap that we saw in the bias between wave height in the wave response to the forecast. So the switch to her X should be an improvement. That's all I have. To thank you for sticking around through all of these presentations. And if you have any questions, please let me know.
Thanks so much, Kaelan. Excellent job. Loved your talk. Please, anybody that's got a question or a comment for Kaelan, raise your hand and I can unmute you, or feel free to enter it in the chat box. And that also goes for any of the presenters this morning. We can go back after we're done with Kaelan's questions. We can go back and ask any others that you may have. Ayumi asks, nice talk, perhaps I missed it, but what precipitation product is forcing the National Water Model V2 for Lake Champlain area? Is it the GFS? Do you want me to read that? Let me know if you want me to read that again.
No, I got it. That's a good question. Yeah, I'm not sure which precipitation model is forcing the National Water Model. I'm not even gonna make a guess because I really don't know. The flood forecast. Yeah, the flood forecast is certainly her switching over to GFS, so including both of them. But yeah, I don't know about National Water Model specifically.
Yeah, if anybody, if Dima or James want to raise their hands to answer that question, I can unmute you. Yeah, Dima, go ahead.
Yeah, Ayumi, this is actually uses both. Again, on the short scale, time scale, uses her precipitation and then switches to GFS after her is done.
Great, thanks, Dima. Okay, we have another question from David Wright. He says, awesome job, Kaelan. How well is the lake represented in the land water mask in GFS?
Again, that's a really good question. So we didn't dive into how the models are treating the lake, which would be another great diagnostic step for seeing possibly why the precipitation performance and why the wind performance are as they are. That being said, we're assuming that it's not great because, as we saw with those grid points, most of them aren't even falling over lake. So basically, we're thinking that that GFS is not blind to the lake being there, but certainly not representing it in any realistic way.
Okay, thanks, Kaelan. Dima, did you have? This might be a hand up from the previous time, but Dima, if you had anything to add, feel free to unmute yourself. You've got the power to do that.
No, I don't have anything. It's just probably leftover.
Yep. Okay, I'll put it down now so I don't get confused again. Okay, let's see. Greg Lang asks, he says, hi, Kaelan, wondering if your results for wind directions include the east-west rotation / correction of her and her X.
They do indeed. They do indeed.
Okay, great.
Yeah.
Thank
so to clarify, the GFS grid, as you can see, is the grid is lined up with latitude and longitude lines, but her is not. So there's about I think it's about 15 degrees. The grid is offset over Lake Champlain. And so when you do the analysis, you have to correct for that small amount of shift.
Okay, thanks. David and Ayumi both say thank you for answering their questions. And Dima had previously typed in a comment, excellent talk, Kaelan, and great contribution to the project.
Yep.
Greg Lang also says great thanks and great talk. Okay, so I'll pause here a second to see if anybody else, looks like we've got a hand up here. Let me see if I can. All right, Jia Wang, I'm not sure if this is actually a real hand this time, so I've unmuted you, Jia, if you've got a question. I suspect he's having some technical issues on his end. So give it a second. Okay, Joe, I'm going to go ahead and remute you. If you've got a question, please type it in. And if anybody has something remaining questions for Kaelan or any of our fellows, please feel free to. Joe, I've unmuted you again. I see your hand going up. I think that's a phantom here. So, okay. I'm not seeing anything else come up. So, Kaelan, I'm going to go ahead and thank you again for a wonderful talk.